Welcome back, everyone. In this very short video, we focus purely on the mathematics of finite horizon dynamic programming. No stories, no examples, just the very core optimization setup and the steps that lead us directly to the Euler's equation. We want to maximize utility over a time period from time period 1 till t, and it is subject to a constraint. Um, the control variable in this model is C, which is our consumption, and our utility depends on this consumption. So our utility is dependent on consumption, and our state variable is K, and in the initial time period we are endowed with some level of K, and at the final time period we'll still have some leftover capital. Okay, the first step is to just state the Bellman equation. It is going to be a function of capital at time period t, and we want to basically what this equation tells us is that it just says that the value of having capital at time t is equal to the maximum of these two things. Firstly, the immediate utility you get from consuming at time t, and next the continuation value of the capital you carry into the next time period. So basically the decision maker chooses, therefore, through the resource constraint, to maximize the sum of today's utility and tomorrow's value. The key point to remember is that whatever you consume today gives you utility now, and whatever you don't consume becomes next period's capital, which also obviously has its own value. And this recursive structure is what allows us to solve the problem backwards, starting from the final period and working our way back to the first. So I'm just going to talk about the mathematics of this, and the step one is always to identify the control variables and to take the derivative with respect to the control variable, and then you just put it equals to 0. In our case, the control variable is consumption. So I'm going to take the derivative of the value function with respect to C, and I'm going to take the derivative of u, which depends on C, and then the derivative of v t plus 1, which actually depends on kt plus 1, and kt plus 1 depends on ct. Okay, so the expression on the left is just the derivative of u with respect to ct. This is the derivative of v with respect to kt plus 1, and the derivative of kt plus 1 with respect to c is just a minus 1. So I multiply this by a minus 1. Since we want to maximize the value subject to the control variable, I have to put this equals to a 0. So this is my expression. I want to take the derivative with respect to the control variable and put it equals to a 0, and therefore I'll have the derivative of utility with respect to ct being equals to the derivative of the value function with respect to kt plus 1, and I'm going to call this my equation 1. Okay, the next step is to identify the state variable, and then you take the derivative with respect to the state variable. In our question, the state variable is kt, so I'm going to take the derivative of vt with respect to kt. The utility function does not depend on kt, so the derivative with respect to kt is just going to be equals to a 0. This actually does depend on kt because kt plus 1 depends on kt. So we're going to take the derivative of vt plus 1 with respect to kt plus 1, and then kt plus 1 is what actually depends on kt. So we have the derivative of v with respect to kt is equals to derivative of vt plus 1 with respect to kt plus 1, and the derivative of kt plus 1 with respect to kt is just a 1, right? So that's just a 1, and yeah, that's my equation 2. Okay, we have two equations now, and to get the Euler's equation, I want everything just in terms of utility. Okay, so the first equation that I had was the derivative of utility with respect to CT being equals to the derivative of the value function at kt plus 1. And I can see if I put this the equation 2 right here, then I'll get v derivative of v with respect to kt. Okay, and let's lag this equation, the first one, ct is equals to this. Let's lag this behind by 1 period. If I lag it behind, I'll get the derivative with respect to ct minus 1, and it's going to be equals to the derivative of v with respect to kt. Okay, let's call this my equation 3, and let's call this 4. So I want to divide 3 by 4. ct minus 1, and this is the value at kt, the derivative of at kt, and this cancels out. So we have a 1. And this is the Euler's equation. So this expression is the Euler's equation. And it basically tells us that the individual tends to do consumption smoothing. So the individual does consumption smoothing. Okay. Okay. Oh my god, I did not spell it right. Okay. But Euler, I did spell. Yeah, that's right. Okay, there's yeah, that's everything that I wanted to cover in this lecture. But another thing that we can add to this lesson is that the kind of there can be some deviations to this equation that they might give you in an exam. For instance, they could change, make a little bit of changes. For instance, they could add, for instance, a discount factor. So let's call the discount factor delta power t, and it could be that they've not given you uh, k, like it could be k power alpha or whatever. So maybe it's just some kind of function that depends on kt. So again, in such a scenario, we're going to follow the same steps, right? But the Bellman equation itself should change. So the Bellman equation, I'm just going to copy paste it, has to change because now there's a discount factor in our equation. So the Bellman equation, as you can actually guess, that the future time periods are just going to start, we're just going to start discounting them. So that's the only difference. The remaining procedure is the same. So this brings about the end of this short lesson. That's basically the complete mathematical pathway to the Euler's equation for a finite horizon problem. Keep this mind in structure structure in mind. Sorry, it's the foundation for most dynamic optimization models, so it's pretty useful. And take care for now. I'll see you in the next lesson.